So the titles may be a little bit more provocative than the actual talk. I just want to make sure Stephen's paying attention over there. And really what I wanted to talk about was kind of an inflection point that I think that we're coming to as a community and what my lab's been doing to try to develop the types of models that I believe that we need in order to make sense of the growing data that we're seeing. So just kind of a broad idea, my lab aims to use the statistical structure of data to improve both data acquisition and data modeling. And on the data acquisition side, there's, like these are pictures that you've seen many, many times. I'm putting it here for familiarity so that you can feel at home. But the idea is, like we're getting more and more neurons, We saw yesterday in the keynote, which I will refer to again. It set me up beautifully, actually, so I'll refer to that a couple times. But we're seeing, from tens to hundreds to thousands, and not just thousands and thousands of neurons in the same area, People are putting 8 neuropixels, Carlos Brody's octoprobe experiments, 8 neuropixels all across the brain. And so we're really seeing brain-wide data. And I'm guilty of helping with this data explosion too, So my guilty pleasure is doing signal processing. That's where I came from. We have a lot of work in the lab trying to make this problem worse. And I thought that once we get all this data, we'd have the tools to interpret them and to draw nice biological conclusions from really large-scale, data all over the brain. But once we started looking at this data, what people saw was this everything everywhere kind of issue, Not as opposed to, oh yeah, like visual information is nicely, compact here, and motor information is nicely compact here, There's correlates all across the brain, and we're seeing this in a number of different ways now, There's a number of papers showing behavioral information in early sensory cortices. Actually, my lab's been collaborating with Patrick Hinold's lab, looking at that type of information, early auditory processing. Here I just kind of picked 2 examples that I particularly like. So one is from Jennifer Lee's lab. This is this middle picture from zebrafish. They have amazing microscopy setup where they can follow with light sheet microscopy freely moving zebrafish and try to get place information and understand where place information is in the brain. And while it's highly concentrated in some areas, it is also spread out throughout the entire brain, So you have the bright spots are neurons that are single neurons that are highly tuned to spatial locations, It's a measure of placiness, if you will. And it stretches throughout the entire brain. Maybe data that you might be more familiar with for those of you who work with electrophysiology and mice, Nick Steinmetz's work looking at decision-making tasks, neuropixels all throughout the brain. You see correlates of engagement, correlates of visual, correlates of motor, correlates of everything everywhere. And the question is, what do we do with this? So I want to also, be set up nicely by yesterday's talk. So the classic view when we think about brain-wide data is that anatomy is the thing to think about, Where are you recording? What are you recording in the terms of behavior? And how does that relate? And so, this is a puzzle. This 5 senses puzzle is a puzzle my kids do. It, very nicely in the middle has a nice picture of a brain, and it shows you where in the brain every single sense is. So from an early age, they get indoctrinated and they understand that brain area equals function. And this continues, So this bottom picture is what my puzzle that my grad students work on. But the same idea, And what we saw yesterday, what we're seeing constantly is that while this is informative, it is not complete. So, I think that we need to revisit some ideas that have been around for a long time, like parallel distributed processing. I had the distinct pleasure when I was in Princeton of being down the hall from John Cohen, who I guess indoctrinated me into a slightly different set of ideas related to how, rather than thinking of hubs localized in the brain that communicate with each other, it's really just a bunch of distributed modules that are everywhere, but are related to a particular task, even though they're distributed, And I'll try to get a little bit more into that when we start getting into actual math. And I don't think this should surprise anyone, right? So I also picked two examples. It's I guess a thing I do. But here's two examples just kind of showing this idea, in addition to what you saw yesterday very beautifully, right, in the speech areas, right? So one is from Alex Hook's lab. You inactivate LIP. You ask the monkey to make a decision. Guess what? It does just fine. On the right is some really beautiful, a series of work from Marina Bedney's lab down at Hopkins, where she looks at congenitally blind patients, and you get all kinds of things showing up in visual cortex, things like language and math, right? And it's really, I think, making the point that this is a highly distributed, very interconnected system. So I think that we're, given this data, we have an opportunity to kind of break free of this single area processing paradigm and really think about a brain-wide functional architecture, right? The software that runs on the anatomical architecture, the hardware that we traditionally think about. And of course, these two things are related. I don't want to come off as being an anti-anatomy person. I am not. I'm just saying that there is an extra level there of how the software is structured relative to the hardware. And we now have the data to look at that. I will say that there's three properties that I consider as being essential to this endeavor. So we talked about distributed, we talked about modular, right? There has to be some sort of structure there, or else we're all kind of screwed and there's no data analysis that will save us. The last thing is time varying, and I think this is quite crucial as we learn more and more about neuromodulators, about the rates of synaptic plasticity. We have some work with imaging work of imaging single spines at the level of AMPA receptors, right? So we can image individual AMPA receptors day after day after day in vivo. This is with Austin Graves and Rick Huganier down at Hopkins. And 50% of synapses change every day. And the mouse isn't learning anything that we can tell, right? I mean, unless it's contemplating life in its home cage and working out whatever Plato's paradox, but highly doubtful. So I think that all of these are essential pieces. And I stole the slide from Memming, so I want to give due credit where credit is due. This is a beautiful list. Is a little outdated now, but I'll have to get back to him so he can make me a better one. This is a list of all kinds of dynamical systems that operate, and if we think seriously about dynamics as computation, so thanks Emily for setting that part up, then we need to think of how to model this modular, time-varying, and distributed these properties. And what I think is missing in a lot of models is that most models, while they might be time-varying or while they might be modular in some sense, many of them are not both. They don't capture both processes. And the modules are often anatomically defined. And so we tried my lab has been trying to generate a model that will hopefully start to answer some of these, develop a model that captures some of these properties. So I want to go back to basics, right? Basically rethink the problem starting from fundamental assumptions. Right, so I'm going to make two assumptions, and I hope that they're not particularly onerous assumptions for anyone. If Stephen, if you feel upset by anything, just raise your hand. So the first assumption is that the brain is a dynamical system, in that the state of the brain, defined by the neural activity at time t, will influence the future states of the brain. Just that, right? And I think that the evidence for that is widespread, including the talks that we just saw this morning. So I hope that that's not controversial. The other that maybe is a little bit more controversial, depending on how much time you spend on Twitter, is that there's a neural manifold, and that the actual set of states that matter to the brain is much lower dimensional than the number of neurons, essentially, right? So there's a lot of high-dimensional nonlinear correlations that tell you that there's a surface that you have to adhere to in order to be like a normal, healthy, functioning circuit. So if you have these two things, right, what do you get? Oh, and I will say, This does not have to be in the neural space. This can be in the latent space. So in our particular model, what I'll show here is we've been modeling everything in a linear latent space, meaning that the actual data that we observe, y, at time t, which is some measure of neural activity for every neuron, is equal to dx, where d is a set of ensembles, basically. It's essentially a set of latent factors that are describable, and the weights x are the latent dimensions that the manifold is evolving over. We choose linear for a very specific reason. We do not want to destroy the geometrical structure of the data. You put nonlinear things in, you can bend the manifolds in all kinds of ways. And that's great if you're doing something like a Koopman operator and you want everything to be linear. It's beautiful. Not great if you want to model the geometry. So we're going to stick to linear here. I'm very open to hearing opinions on other types of geometry preserving nonlinear stuff. I'll be around all today and tomorrow. So once we have this idea of a neural manifold and trajectories on a neural manifold, what this means is that there exists a set of functions. Transport operators is a name that you might have heard in the literature. There's a lot of beautiful work, for example, from Bruno Olshausen a couple years back. And you could think of these as operators that, given that you're at a particular point x on the manifold, move you to another point on the manifold. So they can't move you off the manifold. If they move you off the manifold, you've violated assumption 1. So these transport operators effectively describe the ways that you can move and stay on the manifold. Now, what's beautiful about the manifold assumption, and note, I did not specify what the manifold is. I didn't say torus, I didn't say ring, I didn't say anything, because I don't actually care. All I need is local smoothness, because what that allows me to do is define tangent spaces. And once you have tangent spaces, is equivalent to effectively transport operators, except infinitesimally local. So if you're sampling, if your dynamics are being sampled at a very high rate, a tangent space is a pretty good approximation for movement on a moment-by-moment basis. But what's really, really nice about tangent spaces is that they're spaces. So you've gone from a nonlinear manifold to a subspace description, and a subspace description enables you to have a linear decomposition of the directions of motion that you can take. And this is where our model comes in, right? So we use this to define what we called a decomposed linear dynamical system in continuous time or discrete time, right, depending on how you want to model your system. Continuous time is better for longer-term predictions because it more closely adheres to the manifold. However, it requires a matrix exponential, which is a pain in the ass, I think is the official term. However, the discrete case can be run in larger settings, and I'll show you examples towards the end of running it on 10,000 neurons. We've run it on 60,000 just fine and can fit the data. So the model architecture, right, just to kind of summarize, X evolves according to, And so the idea is that these Fs, right, so I'm going to focus on the discrete case here. These Fs are a set of basis dynamics. They are functions, they're a matrix, n by n. And the C's tell you at each time t which F's are perturbing your system. So essentially, the C's steer you in the tangent space towards the direction that you want to move. So the F's are not time varying. They are model parameters that we fit. The C's are variables that tell us instantaneously at each time how you move. The only other assumption that we make here is that the C's are sparse. And the reason why we want this is interpretability. We don't want every single dynamical system to be active at every time. It makes the problem statistically unidentifiable. It also makes the interpretation incredibly difficult. So the way that you could think about C as being sparse is you're trying to align the F's as closely as possible to the actual direction your flows are moving on the manifold. So this is just a schematic of the block diagram. Since I only have about 5 minutes left, I'll just kind of jump into results. I will say that we have a number of synthetic examples and toy examples in the papers, right? So there's this JMLR paper from last year as well as an improved fitting method and extension to the model led by our collaborator down at Georgia Tech, Yen Ho Chen. So I won't get into those. I'm happy to talk about those, but I want to talk about neural data because statistical analysis of neural data. So I'll start with C. elegans, right? So this is led by Eva Jeseritz. It's now a preprint out on bioRxiv. This is not Eva. This is Eva. This is a C. elegans. And so what I want to emphasize here, right? So going from the top to the bottom, you have the actual fluorescence at the top. You have the estimated fluorescence, essentially the reconstruction of the model at the bottom, or the second row. There we go. Second row. These are the latent states. I'm not going to talk about them because I actually think the dynamics coefficients, those C variables, are much more interesting, right? So these are the C variables. And what I want to focus on is how for each state, so the blue lines here are the states of the worm. So you can think of it as like forward, crawl backwards, turn right, turn left. Every time there's a state 3, you get this transition from a purple to a maroon. So there's this slow transition between 2 different forms of connectivity, right? Because remember, the C's are dictating what your interconnections are between neurons, statistical interconnections. Here, right, there's a sharp, you still have this purple into maroon, but you have this extra black thing, right? And what this is doing is essentially saying that on top, riding on top of whatever the natural motor behavior was for this action was something else. And sometimes we could tell you what that is, right? So for example, right around the halfway mark, there's these oxygenation puffs, and you get essentially an additive dynamical system related to the oxygenation. In fact, we could look at the neurons that are considered to be very oxygen sensitive, the bag neurons, and we can plot connections to and from the bag neurons. And we can do this on a moment-by-moment basis because the C's let us reconstruct the dynamics at every single time step independently. And what you end up seeing is that when there's no oxygenation, the bag neurons are effectively not part of the active circuits, no matter what the animal or the worm is doing. When there's the first puff of oxygen, the bag neurons light up immensely, and you can see exactly where they lead to, right? Because instantaneously, the model is linear, even though it's approximating a highly nonlinear, non-stationary process. And then after a few puffs, you see this adaptivity. And the sensory neurons give way to proprioceptive neurons that are leading, right, these yellow lines that are running the show, in order to compensate for the fact that there's a repeated puff that the animal's acclimating to. Another kind of neat thing is that if you look at neurons that have lesser known processes, in particular interneurons, we find that while the activity of interneurons can be the same across multiple behaviors, their connectivity, the role they play in the network, is different. And I think for us, this is an interesting way to think about the difference between thinking of tuning as a tuning of activity versus tuning of connectivity, right? So maybe you can have the same level of involvement into processes, but your role changes. And for interneurons, to me at least, that makes a lot of sense. So I want to just get into the last bit in the last minute. So we also extended this to multi-neuropixels. There's a lot of challenges in that different sessions record different neurons in different areas. And Noga Mudrick, a student in the lab, has done a monstrous amount of work leveraging some of her previous work in ICML to essentially use this DLDS model to stitch together between all these sessions and be able to fit in. And she just, I was very proud of her, she got a spotlight at ICLR for this work. But she can essentially learn these brain-wide dynamics across thalamus, brainstem, hippocampus, right? We get these big systems, and we've been cracking into it, trying to interpret what they are. And I will just kind of end up with this, where we can compare hit and miss trials for the same animal. And I'm plotting the C coefficients here again. And we notice that there's this orange, this C2 shows up reliably on hit trials, but not miss trials. And if you look at what that F2 is, there's all these flows from primary to secondary and hippocampus to secondary motor. And so we're thinking that this could be a module that represents reading out information into an action when the animal's making a decision. And so we're very excited to dig more into this. So the initial analyses are in that ICLR paper. We're digging more into it. And since I'm out of time, I'll just say we've also started doing this on zebrafish. We can fit it with an R-squared of like 0.9, 0.89 on 10,000 neurons. And we see much more complex dynamics, but we're really excited to dig into this. So with that, I would like to thank my lab. May God be with the funders. And thank you.
All right, there'll be lots of time to chat with Adam, so maybe time for one quick question if anyone has a quick one. Otherwise, we'll move. Okay, Guillaume.
Do I understand correctly that your Cs kind of are completely freely temporally varying?
They can be. We have introduced a smoothness prior that can be turned on and off. We find that even when we turn it off, they're pretty smooth.
But isn't it the case that your manifold picture at the beginning suggests that they should actually be conditionally independent of time given the time varying state, that they should just depend on xt, not t itself? Or
No. So you could steer yourself on the manifold in lots of ways, right? If you think of the system as being a static system that is a fixed deterministic system, then yes, xt will dictate the whole thing about the dynamics, right? And you move and you have a static flow field. But we know that there could be changes and that you can revisit the same state, but under different levels of neuromodulation, you do different things. And so we wanted to be able to capture that.
Cool, thanks.